Okay, circular forces, number 2. This is one of the classics, right? Car going through a valley. This is a situation we should be very comfortable with. Car travels through a valley at a constant speed, though not at a constant velocity. Explain how this is possible. So constant speed, but not constant velocity. What's up with that? The velocity is not constant because velocity is speed and direction, because the direction is changing. Velocity is a way of keeping track of both speed and direction. And just speed, that's just what your speedometer says. So while you might have a constant speed, you could have a changing velocity if your direction is changing. That's what's up with that. Construct a qualitative motion map for the car. So as the car goes through this dip, I'm just going to make my motion map right on this. If it's going at a constant velocity, then the dots in our motion map would be equally spaced out along this road, right? Because it's going at a constant speed. And then make our little arrows pointing halfway to the next dot. That's all. So you can see there, that's kind of a visual. The reason why this question is coming right after part A is you can see those velocities changing. Those little arrows represent the velocity. And although they're all the same length, they're definitely changing, right? Is the car accelerating? Yes. What is the direction of the car's acceleration toward the center of the circle? Because it's in circular motion. Now, if you're looking at that and you're saying, like, okay, I don't buy that. Well, first of all, it's true, so it doesn't matter whether you buy it or not. This is actually true. And the thing you need to understand, if this doesn't sit well with you, if you're like, wait, how is it it's going this way, but it's accelerating toward the center? That's true because one of the very, very deep misconceptions that people have that it's so hard to get over when you're doing this introductory physics kind of thing is separating out velocity and acceleration. Those are two different things. So here, the velocity of the car is this way, but the acceleration is the thing that's bending the velocity up this way. If there was no acceleration, it would just keep going straight. And if something's in circular motion, that acceleration has to be toward the center of the circle. We know that that is true. The thing, if you don't like the fact that it's accelerating toward the center because you're like, it's going this way, so it's not going that way. Acceleration is not the direction that you are going in. Acceleration is how your velocity is changing. So if you think about like when we throw an object up into the air, on the object's way up, what is the its velocity is up, right? What's the direction of its acceleration? Down, exactly the opposite direction. And because it's exactly the opposite direction, that has the effect of slowing it down. So those two things do not have to be in the same direction. And when we have circular motion, we know that that acceleration and the unbalanced or net force must be toward the center of the circle. We just know that. All right, construct a qualitative force diagram for the car at the moment it's at the bottom of the valley. So if it's at the bottom of the valley, we know that there must be unbalanced force toward the center. The toward the center has to be the winning direction, which means that the support force or normal force on the car must be bigger than the gravitational force. This must be winning. Are the forces balanced? No. Justify the relative sizes. Fn must be greater than Fg because there must be unbalanced force toward the center. And then finally, if the cars, we got some numbers here, so we want to find the magnitude of the centripetal force acting on the car. What does that mean? This is just, the centripetal force is another way, and when we have circular motion, that's another way of saying the unbalanced force. So we know with circular motion, unbalanced force is equal to mv squared over r. In this case, that is 1200 times 25 squared over 25 meters. Oh, that's 30,000 newtons. Construct a quantitative force diagram for the car. So that's the same as this. I'm just going to use my same force diagram and add in the numbers. So here, unbalanced force is equal to, I know that is winning and that is losing. The force of gravity is just the mass times 10. And I know the unbalanced force, I found that right here. That's 30,000. So 30,000 is equal to normal force minus the force of gravity is 12,000. So this is going to be 42,000. So you can see the difference here. The 30,000, that's the difference between these. Right? That's how you do it. How about this car, going over the hill this time? Construct a qualitative motion map for the car. So I'm going to make my little dots nice, evenly spaced out, like so, and then with my arrows that go halfway to the next one, something like that. Is the car accelerating? Yes. What is the direction? Toward the center. How do I know? Because circular motion. If the speed of the car is 43 kilometers per hour, uh-oh, that is the wrong units, so I'm going to have to do a quick conversion here. 43 kilometers per 1 hour. I would like this to be in meters per second. 1 kilometer is the same as 1,000 meters, and 1 hour is the same as 3,600 seconds. So that's about 12 meters per second. So the speed, mass is 25, determine the magnitude of the centripetal force. Remember, that's just the unbalanced force. If you're confused about that, you can get the last one, then pause here and see if you can do the rest of this just like what I did in the last one. It's important that you try to do those things on your own. So unbalanced force, when we have circular motion, is equal to mv squared over r, mv squared over r. So it's about 6,900 newtons. Construct a quantitative force diagram for the car at the moment it's at the top of the hill. Are the forces balanced? No. Justify the relative size of the forces. In this case, the center of the circle is down here, so gravity has to be winning. Fg must be greater than that because unbalanced force toward center. The reasons are the same. It's just the center of the circle here versus here. I mean, you can tell where the center of a circle is, right? Go back and ask your geometry teacher about that. Just kidding, you don't need to, because you know. Because unbalanced force toward the center. So let's make this force diagram. So force of gravity, and there's the normal force. And notice that I made this bigger. Of course, the force of gravity doesn't change. It's always the same. Gravity does not care about what the car is doing. So same car, 1,200 kilograms times 10 is 12,000 newtons of gravitational force. So now my equation looks like unbalanced force is equal to gravity is winning versus the normal force. So that unbalanced force, which is 6,900 is equal to the force of gravity minus the normal force. Do a little algebra there, and you should find that it is the normal forces. Oh, off screen there maybe. About 5,100 newtons. There we go. And last here, roads are banked. I don't know if you've ever noticed that. Certainly you notice that if you're watching like NASCAR or something, they're like very banked. But even if you're getting off like right here by the high school, if you're going to get on 81 North and you just drive up like you're headed to Walmart there and you get on, you're on 64 for just a little very, very short bit, and then there's that big lazy turn that goes off to the left and puts you onto 81. Pay attention next time you're driving on that, and you will notice that that road is banked a little bit. It's tilted a little bit toward the inside of the circle. Why? So for the situation of an unbanked road, draw a force diagram for the car. So if this car is coming right at us, there's gravity, and there's a normal force. Car's not moving up and down, so those are balanced. And then toward the center, there's got to be friction. If this is pure ice and there's no friction there, then it can't turn. Now that is where the unbalanced force toward the center comes from. Now for the situation of a bank road, draw the force diagram. This is a little tricky. And we're not going to get into doing this like with the sine and cosine and the numbers and everything. It's a little bit more complicated than what we want to do in this section or this unit about circular forces. But I'll show you here what this looks like. And this helps us understand why banking the turn helps the car to make the turn more safely. So the car can make, like, what's the safety issue here? Well, if you don't have enough friction between your tires based on like how fast you're going and how much friction you can get there, then that's when the car might like skid out of the turn. And of course we don't want that to happen. So on a turn that people are going to take at pretty high speed, like that entrance to Interstate 81, we want it to be as safe as it possibly can be. So how does this make it safer? The support force is always perpendicular to the surface, the road in this case. And then the friction force, of course, that can't point right toward the center. It can only point along a road. So in terms of like doing all of the reckoning with this, it's a little bit tricky because we need to figure out, so here, here's my friction force, force of gravity. We know that the forces in the up-down direction are balanced, and we know that the center of the circle, it's not down here, the center of the circle. The center of the circle is actually here. If we had a bank road that was banked all the way around, like a circular NASCAR kind of track or something, the car's going around in a circle around this point, not down here. It's not going to go down to here. right? It's going around this way. So that means the forces in the up-down direction are balanced. So how do we do that? Well, we need to break both the normal force and the friction force into their components. So what's equal to what? Well, the force of gravity and this little bit of the friction force that's down, those would have to be equal to the normal force. So right off the bat, that means that the normal force is bigger than it would be here, right? And bigger normal force, that means more friction, right? Because force of friction is equal to mu times normal force. And this is just some constant that depends on like the tires in the road. So if we tilt it like this, we're going to get a little bit more normal force, which means we're going to get a little bit more friction. And part of the friction force, this part of the friction force is toward the center, and part of the normal force is also toward the center. So what we're doing when we build roads and we bank them a little bit, or you're building a NASCAR track or whatever, we're tilting it so that the simplest way to understand it is that we're making part of the normal force point toward the center of the circle. And that helps get more friction, and it helps us when we have more force toward the center of the circle, then we can go faster and take the turn more safely at a higher speed. Now that's what's going on there. Again, we're not going to do that with numbers. That would be pretty complicated. It's a little bit beyond what we want to do.